Our two special right triangle types are our 30, 60, 90 triangles and the 45, 45, 90 triangles. Remember, you only know that it's 30, 60, 90 if you are given a right angle and a 30 or a 60 degree angle. I have a 60, triangle sum theorem tells me this then has to be a 30 degree angle. Similarly, there's only two ways to know if I have a 45, 45, 90 triangle. Right angle given a 45, triangle sum would tell me this is 45, or the other option is I may have provided not any angle measures, but if I provide that you have a 90 degree angle, so you have a right triangle that is isosceles, then it has to be 45, 45, 90. So those are the two options. Now, how we have been applying these, and then remember, this isn't the only way. You're welcome to go ahead and search YouTube or search Google to find other ways to solve 30, 60, 90, and 45, 45, 90 triangles. The way that I like to approach this, since this follows up right after our similarity unit, is with similar triangles. But I'm never going to give you these extra triangles. You're going to have to remember that for every 30, 60, 90 triangle, like this one, we compare it to kind of a parent triangle. And your parent triangle is what you have to remember. And it's all about the side lengths across from the angle measures. Start with your smallest angle. Your smallest angle is 30. Always across from that 30 is going to be your side length of 1. Your hypotenuse across from your 90 will be a side length of 2, and therefore across from 60 will be your side length of square root of 3. For your 45, 45, 90 triangle, the two legs of that triangle are congruent because it's isosceles and they both have side lengths of 1, which Pythagorean theorem would then prove the hypotenuse is a square root of 2. These are the functions or the triangles that we are going to use to compare every 30, 60, 90 and every 45, 45, 90 triangle. Okay. In doing that, here's what I like to do. I look at this and I recognize right away it's 30, 60, 90. I don't have this to compare it to, that's just in my head. So I think, okay, across from 30 is side length 1, so I'm going to take this side length, which is y, and put it over 1. Okay. Across from my 90 is my side length of 2. I'm going to put the x over 2. Across from 60 is square root of 3. I'm going to put this over square root 3. I want to focus here on any side now that has a ratio that is all numbers, like this. Can I simplify this ratio, this fraction? And in fact, I can. When I simplify this ratio, 6 square root 15 over square root 3, 15 and 3 are both radicands. They are inside my square root. I can divide. 15 divided by 3 is 5. This becomes 6 square root of 5. Now I do want to write it as a ratio because what we're going to do to find x and y now is cross multiply to solve. So I want to set two ratios equal to get my proportions. Now I know that x over 2, and I'm going to highlight this here, I'm using this because this is my ratio that is all numbers twice. I'm going to use it to compare with my x and use it to compare with my y. So x over 2 will equal 6 square roots of 5 over 1. When I cross multiply, I get x is 12 square roots of 5. And then do the same thing with y. Y over 1 equals 6 square roots of 5 over 1. So again, I'm using that 6 root 5 over 1 twice. I could have used 6 root 15 over root 3, but that's going to require me to do more algebra in this cross multiplying and this cross multiplying. If I do it once, I can get rid of it right away. Cross multiply here, y times 1 is y equals 6 times 1 is 6, so we get 6 square roots of 5, and we're done. For the second example, it's a 45, 45, 90 triangle, so I know my legs have a ratio of leg over 1, so leg over 1 and leg over 1, okay. And my hypotenuse is over the square root of 2. Once again, I look and I see that this is my ratio with all numbers. That's the one I'll use twice. It does not simplify like this one did. So I can move right into setting it up as a ratio, as a proportion with both of my other sides. X over 1 equals 8 root 3 over 1, which makes sense. These are congruent. X is 8 root 3. Okay. But then y divided by the square root of 2 equals 8 times the square root of 3 over 1. Now I'm going to do this cross multiplying just to make sure we understand what's happening here. Y times 1 is y, but when I have 8 square root, 3 times square root 2, I can multiply the 3 and the 2. They're both radicands. They're both inside my square root, and I get 8 square root 6. I do always want to look to see if it simplifies, but 6 factors into 2 and 3, those are both prime. I have no perfect square factors. I just get 8 square root 6, and I'm done.